So we are now moving towards the sustainability track, and our first presenter is Kelley and Jasper from Iceotope Technologies, going to talk about the breaking the barrier, chip-level cooling up and beyond 1,000 watt in a single-phase dielectric fluid. Please, welcome.
Hello. Hello. Thank you for joining our discussion today about breaking the barrier, chip-level cooling up to and beyond 1 kilowatt with single-phase dielectric fluid. There's been a persistent perception in the industry that single-phase immersion cooling is limited to delivering chip-level cooling to about 400 watts. In fact, in our OCP immersion cooling working group, we have a series that really focuses on how, with technology, we can break that barrier. So my talk today is really to introduce how Iceotope has broken that barrier, and we'll be discussing those results. And joining me in this presentation is my esteemed colleague, Dr. Jasper Kidger, head of thermofluids at Iceotope, and I'm Kelley Mullick, our VP of Technology Advancement and Alliances. So before we begin, I'd like to spend just a little bit of time on the liquid cooling technology landscape. Historically, there are two types of liquid cooling technology: direct-to-chip or cold plate, and liquid immersion. Cold plate technology typically uses a metal cold plate with either water or dielectric fluid to deliver component-level cooling to the hottest IT components, typically the CPU and the GPU. The remainder of the system is cooled with air using the existing infrastructure within the data hall. Most liquid immersion is done in a tank filled with fluid, and the server racks are fully submerged within the fluid. With immersion cooling, you have the great benefit of heat reuse and removal of the fans from the data center. However, other challenges exist in that the existing blueprint of the data hall cannot typically be retrofit to accommodate the weight of the tank, fluid, and the IT. So we're going to talk about the Iceotope solution, which uses precision liquid cooling with single-phase dielectric fluid in an enclosed chassis. And I'll show you a video about how the technology works.
A small quantity of environmentally safe dielectric coolant is precisely targeted to remove nearly 100% of the heat from the hottest components of the server through an in-chassis manifold. The coolant runs in parallel to the CPUs, GPUs, power supply, and SSDs simultaneously for maximum efficiency and reliability. Heat can be rejected to dry coolers or captured and reused for heating, negating the need for evaporative cooling and water consumption. We enable you to scale up from a single server to multiple racks within your existing air-cooled architecture, freeing up stranded capacity and offering more flexibility within current Whitehall space.
We've been hearing quite a bit today about stranded capacity, and so that is one of the great benefits of an immersive type cooling, is that you can really pack that compute with, or pack that data hall footprint with compute. So now that you've seen how our technology works, let's talk a little bit about AI and how that's dramatically changing the technology landscape. 2023 was really an inflection point where the advent of generative AI dramatically shifted the technology landscape, and now the entire industry is really focused on how do we support AI. AI requires IT components with significantly higher thermal design power, and with that comes the increased ability to cool at the chip level. Figure 1 illustrates the limits of air cooling and where the case for liquid becomes required. Based on data from ASHRAE, air cooling really starts to max out at around 350 watts at the chip level. In fact, Intel's current generation CPU is at that 350 watt level today. NVIDIA's next-gen GPUs are projected to be near the 1 kilowatt max and beyond, where liquid cooling will be required. In fact, we heard from Brian in his talk this morning about how we're going to need 120 kilowatt racks and how are we going to support that. So we really see the need where liquid is going to be required in the data center. But then this begs the question as to how future-proof some of the different cooling technologies are. So Iceotope's solution as to how future-proof are the different technologies really lies in our use of precision liquid cooling technology and our patented heat sink design. On the right is a visual of our heat sink. In the design, the dielectric is forced through the heat sink via a matrix of pins. We leverage the same forced convection benefits as cold plate water-cooled systems with the advantage that our precision liquid cooling system enclosed chassis is a full systems approach delivering superior component level cooling. Furthermore, based on an internal analysis on the 350-watt CPU SKU, our design achieved a thermal resistance at par with some of the best water-cooled cold plate designs, nearly matching the component level performance. And my colleague Jasper will talk to that in the next few slides. Lastly, our technology is sustainable. We deliver up to 40% reduction in data center OpEx, mostly via removal of the fans. The fluid that we use is cosmetic grade with 0 GWP, is non-toxic, and is reusable and recyclable. We see a reduced carbon footprint due to the ability to support more compute per square meter, and we see up to 100% of the removal of the heat, with that heat being able to be reused in a good fashion. Now I'll turn it over to my colleague Jasper to talk about our test.
Okay, thank you, Kelley. So my own background, I'm a CFD person. I've been doing that for about 25 years now. I knew how this was going to perform, because I'm good at it. But people never believe the CFD answer, and they want to look at the lab data. So we were given the challenge, and so what we've got in my hand is a heat sink that Kelley introduced. The image you can see on the screen, we put this on an Intel Airport Cove TTV. That's for the 4th generation Sapphire Rapids processor family. Why? Well, the most powerful Intel chip of that family at the moment, 350 watts. The Airport Cove TTV, you can run much higher. You can run it to 1 kilowatt and beyond. And we wanted to know not, will it cool today's devices? We know it can. But the question is, how future-proof is it? So what you can see in our test stand there, under lab conditions, we can feed this heat sink with our dielectric coolant at a lab-controlled temperature and flow rate. And while we're doing that, we're monitoring on the test stand the case temperature on the TTV. We're monitoring the temperature on the base of the heat sink. And to be clear, all the numbers I'm about to show you, they're going to be based on the case temperature of the TTV. So we're including the thermal resistance of the tin and everything we're about to show. So, Kelley. Quick chat about the lab test stand. I'm not going to dwell too much on it, but if you want to catch me later and go in more detail. Those of you familiar with the Airport Cove TTV know there are 4 component dies underneath, and that's why I've got a bank of 4 power supplies intermittently feeding each one. The heat sink you saw on the last slide, that's in the middle, the top chamber. And below that, we've got a circuit that's giving us circulating the dielectric fluid, controlling the temperature, accurately measuring the flow rate. And then the heat rejection is through the lab equipment you're seeing on the left. So let's go to the numbers. Kelley. And again. So what happened? So we ran this 1 kilowatt going into the Airport Cove TTV. The temperature we're feeding the dielectric into our heat sink was an easily attainable 40 centigrade. No need for any chilling here, easily achievable value. In this case, we're feeding the dielectric at 7 liters a minute. A quick comment on that flow rate. Remember that flow rate, that's the dielectric flow rate. That's circulated by the pump within our chassis. In your mind, decouple that from the much lower water flow rate you might be used to a water-cooled cold plate. It's not a fair comparison because we're reliant on the dielectric pump to feed our heatsink. Well, how did we do? You can see case temperature, 78 degrees. Typical silicon device, you're usually good for about 85 degrees on the case temperature. Thermal resistance, less 0.04 Kelvin per watt. So this is really, they're cold plates that can't compete with that, water-cooled cold plates. And remember, that value is not just our heatsink, that's including the complete stack-up going through the TIM. If you'd like to see any more, we've got a paper, white paper on the website. Have a look through that. And you know what, at this point, I'd gone away happy because I knew how it would perform. Simulation told me how it would perform. We did the lab test. The results were brilliant. We're cooling something 3 times more powerful than the most powerful chip in the Sapphire Rapids lineup. All was good. Or so I thought. And then the company management said to me, come on, Jasper, we can do better than that. 1 kilowatt. Let's look a few years into the future. Can we get more power into it? What we're going to say for the first time today, what we've not said prior to now, is we've done some 1.5 kilowatts. Same test setup we looked at before. True, to keep the overall case temperature manageable, we dropped the inlet temperature a little bit. We increased the flow a little bit, but it's the same thermal resistance, effectively, we were looking at before. The 2 graphs at the right-hand side, they're showing, the top graph is showing what happened to the temperature, the case temperature, as we increased the power. The bottom graph, that interests me more as an engineer, that's our thermal resistance. You can see on that graph, we've increased the power, so left-hand side, we're down to 300 watts of the real device, moving over to 1.5 kilowatts to the right. It's flatlining. Why is our thermal resistance flatlining? It's because fundamentally, this is based on forced convection. We've engineered a system, we're in tight control of the fluid flow going through this device. And it doesn't take much imagination. We could work to much higher power than we've got there, equipment permitting. So what's the point we're trying to convey here? There's a debate in our industry as to not just how do you cool devices of today, but which of these liquid cooling technologies are future-proof 5, 10 years or more into the future with the demands not only of the processors, with GPUs. And what we've clearly shown on this work is that you can use dielectric cooling with the precision control, the precision liquid cooling, and very much be future-proof for tomorrow's devices. Thank you. Kelley.
Let's take a look at some of the innovations developed by Iceotope leveraging this ability to cool at the 1 kilowatt and beyond level. So on the right-hand side, we have an open view of the interior of our precision liquid-cooled enclosed chassis, and on the left-hand side, we have the rack view of the OCP-compliant rack. Each chassis today can support up to 3.5 kilowatts of IT load, and our rack can support up to 16 chassis with a total of 56 kilowatts today. This solution can be easily scaled depending on the data hall needs and can sit right next to an air-cooled or other liquid-cooled unit. I'm also happy to share with the community the development of the first power supply unit designed for liquid cooling. When Iceotope first started designing liquid cooling in an enclosed chassis, we quickly realized that many off-the-shelf air-cooled power supply units would not be able to support the dense IT loads our technology can handle. So with funding from the British government, the team developed the first AC/DC 3OU power shelf in an OCP-compliant design. This power supply unit can deliver up to 80 kilowatts of power per rack. In conclusion, I hope we've been able to share with you why precision liquid cooling is a demonstrated technology to support the dense AI workloads now and in the future for the 1 kilowatt and beyond chip cooling requirements for next generation CPUs and GPUs in a sustainable fashion. Furthermore, single-phase liquid cooling with hydrocarbon-based dielectric fluids has a long runway, and with technologies such as precision liquid cooling, we have now shown that the 1 kilowatt barrier has been broken. As we look to the next challenge, we know that AI is completely changing the game for data hall cooling requirements. Operators need to know that they are future-proofing their infrastructure investment and that the investment in liquid cooling will have a long runway. Selecting technologies that can meet the demands of processor and chip roadmaps as well as future server generations will be key. So my call to action is really, we need to continue to collaborate, solve difficult challenges, break perceptions and limitations with data-driven results, and collaborate in groups such as OCP to identify the challenges, propose standards, and develop reference architectures, all with the goal of advancing the adoption of liquid cooling in the industry. I'd like to just quickly acknowledge the Iceotope team that participated in this work, and Alex and Neil are here in the audience. And also, I just wanted to show some of the Iceotope team. On the left is a photo of the team that supported one of our enclosed chassis racks at the Mobile World Congress in a partner booth. And on the right is the Iceotope team in the lab where this testing was done. Thank you very much, and I'm happy to take any questions.
Thank you so much. Our next speaker, please get prepared. So, do we have a question?
Yes, hi, Rolf Brink, project lead for the Immersion project as well. Question I have is, this heatsink design seems very interesting, very intriguing. Are you guys considering also tank-based immersion systems in combination with this kind of forced convection? And if so, are you guys also looking at ways of making this technology available to the larger industry?
Yes, so in terms of the tank-based solution, our technology is really focused on the enclosed chassis, although we have seen some collaborations and some advancement of tank-based solutions from the liquid cooling working group. And in terms of making the IP available, these are OCP compliant designs, and so you would just work with us to understand what your data hall needs or IT needs are, and we would provide those.
All right, and
Kelley,
thanks for showing a good line on breaking the ceiling, guys.
Thank you.
And if I could just add a little bit to the answer, I think technically one of the things we're showing is it's the difference between are you working with forced convection or natural convection as a heat transfer mechanism. And so that's where I think one of the key differences lie here.
Okay. Thanks for your presentation. I have a quick question. Did you compare energy usage for air cooling, compression between liquid cooling and air cooling, power consumption?
Yes, and we've done that not just here, but we've done that on many of our projects. And you find that the power needed to circulate the dielectric in the pump is much, much lower than the power needed for fans for equivalent cooling. Okay. So even when you look at the total technology stack up, the pumps in the chassis, the pumps in the CDU, it's still a significant energy saving. Well, on a larger deployment we've got down to a PUE of 1.04 on this liquid cooled technology.
Okay, thank you.